Hi everyone, welcome back to the channel. As you know, in our previous video we saw the key differences between fine-tuning and prompt tuning techniques. We also saw a few prompting techniques such as zero shot, few shot. So I thought in this video just to cover fine-tuning techniques. So the topic for the video is to tune the large language model using PEFT and LoRA method. This method is very famous and very efficient method, so let's explore that in this video. The first I will introduce these techniques, why they are important, and the second half of the video we are going to see the actual implementation of the methods. As you know, fine tuning is a process of retraining a pre-trained large language model on a smaller data set, domain specific data sets, and this actually helps the model to specialize in particular task, okay, and it also improves the accuracy. So what are the advantage with this is the model gets better at a specific task, and second is it improves the performance. The model adapts the better than the generic pre-trained model. And there is also some limitations on the other side. It's time consuming, it's overfitting risk, which means like model may memorize some data rather than generalizing, and there is also high computational resources. And there are few fine-tuning methods that I have mentioned here: PEFT, LoRA and QLoRA method. So it's a time to see LoRA and PEFT, why we are using this method and what are the advantages. So let's discuss each of these key challenges or features and see how LoRA addresses them. So first one is a full fine tuning is computationally expensive. Why it is expensive? Because it needs expensive GPUs and it needs days and days for model training, and it also consume high level of energy. Of course you can think of training GPT model, so full fine-tuning is not affordable. So LoRA is the method which gives us a faster and more efficient way to tune the model. And the second point is like storage and deployment challenges. Even after fine-tuning, full models are huge, okay, some takes up like hundreds of gigabytes, right? And for deployment and storing them is really logistically expensive. So for example, a fine-tuned large language model over 300 gigabytes makes it difficult to deploy on regular cloud servers or edge devices. That's why full models are huge, hundreds of gigabytes. So LoRA stores only in small adapter weight, and so it reduces the requirement of storage and deployment, and that's why LoRA is the best solution. The third point is PEFT makes fine-tuning efficient. So PEFT is parameter efficient fine-tuning, is a method like LoRA and QLoRA and adapters that optimize fine-tuning. So instead of modifying entire model, PEFT actually allows us to keep base model frozen, train only small specialized layers, and enable faster and cheaper fine-tuning, and that's why PEFT is the most efficient method. Another point is LoRA enables multitasking. If you want to train your AI model on multiple tasks, okay, so you have to fine-tune separate tasks, separate models, one for each task. So with LoRA you can fine-tune multiple tasks on single base model. Imagine you need to fine-tune your model on writing a legal documents, then second task is summarizing financial report, third task is helping with a medical diagnosis. So instead of having three different models, you can have just one, and all these tasks can be included in one based model. Then next point is reduces trainable parameter. As I said before, it's like if you do full fine-tuning, it modifies the billions of parameters of the model, and that's why it makes the process slow. But LoRA actually changes a few parameters of the base model, and that's why the speed is higher than the full tuning model. The next point is avoid catastrophic forgetting. Huge problem with traditional fine-tuning is a catastrophic forgetting, where the model forgets old knowledge while learning new information. So if you fine tune a chatbot for legal advice, it may lose general conversation ability. So LoRA solved this problem as well by keeping the original model frozen and adding small task specific adapters during tuning. And the next and the last point is like it brings fine tuning to consumer CPUs. Before LoRA and PEFT, fine tuning required expensive GPUs, okay, that cost like thousands of dollars per month. And now with LoRA you can fine tune LLM on NVIDIA GPUs and even on Google Colabs. I hope you understood why the method is very important. Here I have listed some references. These references are also available in description box. And now it's the time to see the practical implementation of large language model. So as you can see, I have opened Google Colab, and in this notebook we are going to tune large language model using PEFT and LoRA method. But at the same time we are also going to see the full fine tuning large language model result, and we are going to compare that with a PEFT LoRA tuned large language model result. So what we have in the agenda is, first we are going to install the necessary libraries, and afterwards we are going to load those essential libraries. These will handle everything from data processing to model fine tuning and evaluation. Afterwards we are going to load data set. After that accessing model and tokenizer. Then we are going to see number of trainable parameters of LAN-T5 base model. So for this experiment we are going to use LAN-T5 base model. Afterwards we will see fine tuning using PEFT LoRA technique. That's the main goal of the video. The next thing that we are going to cover is a training PEFT adapter. So this process updates only the specific parts of the model, and it helps us to achieve high performance while minimizing resource usage, okay. And at the end we will evaluate the model to see how well it has trained from our data set, and this will give us a clear idea of its performance. So to get started, let's install all necessary libraries required for fine tuning our large language model. We will install dataset for handling data, transformer for working with pre-trained models, PEFT for applying the LoRA fine tuning method, and additionally we will set up, evaluate and root score for accessing model performance, and of course torch and torch data for deep learning capabilities. So let's run this installation and set up our environment. Now that our libraries are installed, let's import them in the project. We will bring an essential tools like pandas, numpy for data manipulation, and torch for deep learning. So from transformers we will load functions for tokenizer, model handling and training. We are also importing PEFT specific models like LoRA config and get PEFT model to enable LoRA based fine tuning. And lastly, evaluation will help us to measure the model performance. Next, let's load our dataset from Hugging Face. We are using dialog sum dataset. I will give the link of this dataset in the description box. There is also one paper published on this dataset. That link will also be provided in the description box. So about the dataset, it is actually designed for dialog summary tasks, and this dataset will help us train the model to generate very precise summaries from longer conversations. Using the dataset function, we can easily access and prepare this data for fine tuning. Now that we have already loaded the dataset, let's take a quick look at it. So what we did, by calling dataset_dialog, we explore its structure and get an overview of the dataset, and this will help us to understand the formats and content of the dataset before we dive into the processing and fine tuning. So after loading the dataset, next two most important things are model and tokenizer. So let's load our pre-trained model and tokenizer from the Hugging Face platform. We are using the FLAN-T5 based model as a pre-trained model from Hugging Face, which is great for sequence to sequence tasks like summarization, and we load the model with auto model for sec to sec LM function and specific bfloat 16 for efficient memory usage. Along with that, we initialize the tokenizer, which will help us to convert text into tokens that the model can understand during the training. So if we pass this, we cannot pass as it is the string to the model, and that's why tokenizer is important. It, as I said, it converts the text into tokens, and then only it is useful for the training purpose. So before we start fine-tuning, let's check how many parameters in our FLAN-T5 based model are actually trainable. And in output you can see that FLAN-T5 base model has total of 247 million parameters, and currently all of them are trainable, because here we are not using any method like PEFT and PEFT LoRA method. This means that 100% of the model's parameters are said to be updated during fine-tuning. Okay, so while this gives us a full control over the model's learning, it can be computationally expensive. So before we fine-tune the model, let's see how well the fine-tuned FLAN-T5 based model perform in zero-shot setting. To learn more about this technique, I have created one video which is available on this channel. Here we will take a random dialog from the test data set, and we will create a simple prompt asking the model to summarize the conversation in 3 lines. Okay, and the model will generate a summary without any prior fine-tuning, because it's a zero-shot setting. Okay, so we are not providing any example here. So we will then compare the output of the actual summary from the data set with the output after fine-tuning. So in the output you can see that is generated from zero-shot test. You can check this conversation later on, but here what is my conclusion is that zero-shot summary from our FLAN-T5 based model isn't quite accurate. Okay, because it repeats the parts of the conversation, and so it fails to capture the key messages of the dialogue. Okay, and this is actually highlights the need for the fine-tuning. And to prepare our data for fine-tuning, we need to tokenize it. So first is tokenization. So here we define a tokenize underscore function that formats each dialogue into a prompt and pairs it with its corresponding summary. This function actually encodes both the input dialogues and their summary into numerical IDs. We apply this tokenizer across all data splits. So 3 data splits or data sets we have: training, validation and test set. And after tokenization, we remove unnecessary columns to keep only the essential data for training. Okay, to speed up the fine-tuning process, reduce the computational load, we will then filter the tokenized data set. So here we are keeping only every 100th example from the data set using simple filter function. And this creates a smaller data set that is actually ideal for a quicker experimentation. Now that we already filter the data set, let's check the size of each split. By printing out the number of samples in the training, validation and test sets, we can confirm that the data set has been successfully reduced. The next is, let's take a quick look at our tokenized data set to ensure that everything is properly formatted. And by printing the data set, we can verify each example now consists of input ID and labels, which are important for training. Before we start fine-tuning, let's set up an output directory where all the training results, model checkpoints and logs will be saved. Now let's set up the training parameters. We defined key arguments like output directory, learning rate, number of training epochs, weight decay for regularization, and logging steps for monitoring progress. Here we are running just one step as a quick test. Once the parameters are set, we initialize the trainer class with our Flan T5 base model along with the training and validations datasets. Now it's a time to see the training process. By running the training function, we begin fine-tuning our Flan T5 base model using the PEFT LoRA technique. Since we have set max step is equal to 1, this will perform just a single training step. It's perfect for quick training, quick testing. And in the output you can see the training process has successfully completed one step, and we can now review the result. The training loss after this initial step is 47.25, which is quite high. The output also gives us an additional performance metrics such as the runtime, training speed, total floating point operation. Now let's set up our LoRa low rank adaptation configuration for more efficient fine-tuning using PEFT method. Here we are going to define key parameters. R is equal to 32, which means it sets the rank for a low rank adaptation matrix. Okay, LoRa alpha is equal to 32, which controls the scaling factor and helping stabilize training. The next parameter is a training module, Q and V, which focuses on fine-tuning the query and value layers of the model's attention mechanism. LoRa dropout is equal to 0.05. Actually it applies dropout for regularization, preventing overfitting. And the last parameter is a task type, sec to sec LM. It specifies that we are going to work on sequence to sequence language model task. This setup actually allows us to fine-tune only a small subset of parameters. Now we apply LoRa configuration to our Flan T5 base model using get underscore PEFT underscore model function. This method actually integrates the LoRa settings, which enables efficient fine-tuning by focusing only on specific layers of the model. After applying LoRa, we can check the number of trainable parameters again, and in the output after applying the LoRa configuration we can see the updated count of trainable parameters. It's unlike before when 100% of the model's parameters were trainable. LoRa actually significantly reduces this number by only updating specific layers like query and value metrics. Now it's a time to fine-tune our model using PEFT LoRa adapter. We start by setting up a new output directory specifically for this training run, and in the training arguments we enable auto find batch size for a automatic batch size selection, set a learning rate and specify one training epoch. As this is a test run, we will limit a training to just one step. We will then initialize the trainer with a PEFT configured model and the tokenized training dataset. This setup allows us to fine-tune the model efficiency, which focuses on the LoRa adapted layers for faster and more efficient training. Now let's see the training of our PEFT LoRa adapted model. By running the train function, we fine-tune the model efficiently with a reduced number of trainable parameters. Once the training is complete, we save both the model and tokenizer locally to a directory named PEFT dialog summary checkpoint local. This makes sure that we can reload the fine-tuned model later without having retrained it from the scratch. It's for future testing and deployment. So in the output you can see the training has completed successfully, and the output shows a loss of 48.75 after the first step, and this loss is still high. I know it's expected as we have only performed a single training step. Also, the model and tokenizer have been successfully saved to the PEFT dialog summary checkpoint local directory. These include the important files like a tokenizer configuration, then specific tokens and model files, and this makes it easy to reload and use the fine-tuned model for future evaluation as well as deployments. Now you can see that we have saved our fine-tuned model. Let's reload it for the evaluation or future use. First, we initialize the tokenizer and the base FLANT5 model from Hugging Face, and then using peft.from_print pretrained function, we load the fine-tuned PEFT model from the saved checkpoint, and by setting is trainable is equal to false, we make sure that the model is in the inference mode, which means like it's ready for generating summaries without further training. And this setup allows us to quickly test and deploy the model for real world tasks. Now it's a time to see the evaluation part and compare the performance of our PEFT fine-tuned models. We will take a dialog from the test set and generate a prompt asking model to summarize the conversation. First, we pass the input through the original FLANT5 model and see its baseline output, and then we run the same prompt through PEFT tuned model to compare the result. Both outputs are decoded into readable text for easy evaluation. And finally, we print the summaries side by side. This comparison actually helps us assess whether fine-tune with LoRA has improved the model's ability to generate more accurate and precise summaries. So in the output you can see the output from the original FLANT5 based model is repetitive and it lacks somewhere the context, but on the other hand the PEFT tuned model provides a much more structured and relevant summary. So finally we will see the side-by-side comparison of the summaries generated by the baseline original FLANT5 and PEFT tuned model. So the baseline summary represent the human written references from the data set. The original model summaries tend to be repetitive and as I said it somewhere lack the context, but the PEFT tuned model summaries are really efficient. It's well structured and it's aligned closely with the baseline summaries. The next is we will evaluate both models using Rouge metric, which it measures how closely the generated summary match the human written ones. Okay, we can focus on 3 scores: Rouge 1 for a word overlap, Rouge 2 for 2 word sequences, and Rouge L for overall structure and fluency. So after fine-tuning with LoRA, the PEFT tuned model shows a significant improvement. You can see these Rouge 1, 2 and L metrics. So these results clearly show that fine-tuning with LoRA is really the best method. Okay, so that's all for this video. I hope you like the video. Please subscribe to the channel. If you have any questions, query related to the video, just leave them in the comment section, and I will see you all in the next video.